Hello, welcome back. Integration for year 13's topic, reduction formulas, further maths. This is, I think this is now on the last optional module for Pure. I think it's called Further Pure 2 on the Pearson/edX. So I'm not quite sure where this is actually fits within the other boards at the moment, but it's something which is on the far end of further maths. And of course, you do some of this stuff at university because you in sort of like the maths degrees, first year, first term, you'll probably be doing some reduction formulas, I'm sure. This particular question is a little bit on the hard side. It requires a bit of a manipulation. I've done the other day another one which was very, very similar to this one, and this is just a tad harder. So I just thought to myself, I'll give you another little bit of practice with something which is a little bit more challenging than the normal ones. Standard integration by parts, of course, for reduction formulas. We're gonna just give it a go straight away as we see it and hope for the best. So integration by parts, put my bits up there. I'm going to differentiate the bit that has the n, so that's the bracket 1 minus 2x to the 4 all to the power of n, and I'm going to integrate just the x. Okay, this will integrate to a half x squared, and this will differentiate to, going from the chain, probably better, I'm going to get an 8 minus 8. I'm going to put the n next from the power, and then I'm going to have an x cubed from the x to the 4, and then I'm going to get the bracket 2x to the power of 4 to the power of n minus 1. And I hope I haven't made any silly mistakes up there, because all it takes is just a sign error or a constant or something like that, and everything goes pear-shaped. Okay, let's write our bits. My integration by parts, the product of those two terms, that's for those who are using a formula, your UV if you want. So that is going to be evaluated. So a half x squared bracket 1 minus 2x to the power of 4 to the power of n between the limits of 0 and 1. So that's the product of those two evaluated, so integrated essentially. And then I have always minus the integral of the product of this particular diagonal. Okay, so we got also a minus in here, so that will switch us into a plus. So I've taken care of the minus. I'm gonna have half of 8, which is a 4, and the n is also a constant, so we're gonna put it at the front, 4n in front of this integral, and inside the integral I'm going to have an x to the 5 bracket 1 minus 2x to the power of 4 all to the power of n minus 1 dx. And of course, this will be evaluated. The limbs are very nice. When I put in there 1, this is 1, so I'm going to get 1 half 1, and then I have 1 minus 1. So the bracket is minus 1 to the power of n. Let me just write it like this. So all of that evaluated at 1. Take away the thing at 0 is of course all 0 because of the x squared, so I don't need to write anything else. So the question now is, what do I do with this particular integral? Somehow I need to bring it back to something which looks like that. And the problem is not the power. The power is looking good. It's something which is reduced from n to n minus 1, but I've got the wrong x there. I got an x to the 5. Okay, but note the x to the 5 can be made into an x and an x to the 4 very easily by using the rules of indices. And why do I want that? Is because first of all I need an x in my product. In front of that I need an x. What I'm gonna do with this extra, if you want, x to the 4, we just hope we're gonna do something about it. At the moment maybe we cannot see what's going on. So let's write it and just play detective for a few lines just to suss it out. So this is now 0 to 1. And let me just use a different color pen. Let's put the x to the 5 as an x. And the x I needed because of that. Times an x to the 4 to make up the x to the 5. And then, of course, we have our bracket. And the question now is, okay, what do we do next? This x to the 4 is a real pain. It would have been nice somehow if we can change this x to the 4, because this bracket has x to the 4 inside, to something which looks like that. Okay, can we do that? We can do it in steps. So I'm not going to be rubbing stuff in there. So if you're taking notes, please rewrite the line. So the first step that I'm going to do to balance it, so just check whatever I'm doing is equivalent, is I'm going to put, let's move that x a little bit further to the front, so I'll make some room. And this x to the 4, I would like it to have a coefficient of -2 in front of it. So I'm going to put a bracket, and I'm going to put in there a -2. But of course now this needs to change to a minus, so it's still worth a plus. And because I took a 2 in there, the 4 needs to change into a 2. Just check that this is exactly the same that we had before. If you look at what all of this should multiply, it should multiply to 4nx to the 5. And if you look again at this term times this term, minus times a minus is a minus, 2 times 2 is a 4, we got the n, and that's still x to the 5. So that is sound, and it is correct. And you're going to see now why I've done that on the next line. This is a little bit tough to see the manipulation, but once you do enough examples of this type or similar, then it begins to make more sense. So there's my 0 to 1. There's my x at the front, and now I'm looking at this particular term. Of course, no accident I put a -2 in there. It's not that I've just gone mad all of a sudden and decided to just do crazy stuff. It's because I'm trying to create this bracket. So I'm going to put an extra line here, which I'm going to fill in. So that's to the n-1 dx. And this must be worth -2x to the 4, but somehow it needs that bracket created. Very, very easily. I can put 1 minus 2x to the power of 4, like this. But of course, because I added the 1, I need a -1 to balance it. So if we check, -1 plus 1 is of course cancels, and then it's still worth -2x to the 4, which is what I had there originally. What was my intention for doing all of this? Okay, it should be obvious now what my intention was, is to actually multiply this integrand, if you want. I'm gonna do it up there, I'm gonna make some space, but if you're working ahead of me, look at what is the multiplication. X times -1 times this bracket, and then x times this bracket to the 1, which of course is exactly the same as this, times this term here. And then I will be able to split my integral. Okay, let me make some room, and I will put a lot of detail for this particular one, so we're all happy what is just taking place in there. So this is my -1 to the power of n over 2, just copied, -2n outside the integral. The integral, of course, is 0 to 1. And now we're going to have x times -1 times this bracket here. So it's going to be a minus x bracket 1 minus 2x to the power of 4 to the power of n minus 1. That times that times that. And then I also have a plus x times this bracket times this term. So x, but when I multiply these two items together, it's of course the same bracket, so it's going to raise my bracket back up to the power of n dx. A lot of people at this stage, they'll be putting the INs and IN minus 1s. I tend to be a bit slow with that. I like to put the extra line. I guess when I was a learner myself, I've probably done mistakes a few times and I got burned, and now I learn I always put the extra line, and I advise you to do so as well. So this is just a mere tidy up. So splitting this integral basically into two integrals which resemble what I'm trying to go back to. So this one has a minus there, therefore I'm going to pull it on the outside. So 2n integral 0 to 1 x 1 minus 2x to the power of 4 to the power of n minus 1 dx. And now be careful with the second integral, because of course when I split it, that still has a minus 2n in front of it. So very easy to forget and just go and split and just write that. So minus 2n minus 2n integral 0 to 1 x1 minus 2x to the 4 to the power of n dx. And from this line onwards is just the tedious workings, just basically getting it to a sensible form to be used. So this is by definition my in, but with one less power for my n, so that's going to be plus 2n in minus 1, and this again is minus 2n in, just in, sorry, I beg your pardon, went absent-minded for a second. So that's the same as that. And of course don't forget all of this that we've been equal is of course my in. I need to simplify this a little bit. Probably the best thing to do is to double the whole equation. So I'm going to write 2 lots of in is equal to minus 1 to the power of n plus 4n in minus 1 minus 4n in. Put all my in's on one side because I've got this term and this term here. So it's going to give me a 4n plus 2 lots of in is equal to minus 1 to the power of n plus 4n in minus 1. And of course my final reduction formula, let me write it in green up here, is going to be my in is going to equal minus 1 to the power of n divided by 4n plus 2, and then I'm going to have a plus 4n divided by 4n plus 2 lots of in minus 1. And that is good and sound, and I hope I haven't made any silly mistakes, and I hope you find it very, very useful. We are definitely laughing now.